If you ask a computer to calculate 2030 factorial, you won't get a standard answer. Multiplying 2030 by 2029 down to 1 yields a number so astronomically massive it crashes calculators and stretches past any standard screen. But there is a very specific computable question we can ask about this giant. Exactly how many zeros are trailing at the very end? Every single zero at the end of a whole number comes from exactly one place. It is the result of multiplying by 10. And a 10 at its foundational level is always built from the same two prime ingredients, a 2 and a 5. Our mission shifts from evaluating the entire factorial to searching the numbers 1 through 2030 for hidden pairs of 2s and 5s. To understand a mathematically colossal object, we ignore its final shape and look directly at its microscopic building blocks. To catch prime ingredients, we use the floor function, an algorithm rounding numbers down to the nearest integer. It acts like a sieve, straining out multiples. Running 2030 through a sieve catching 5s reveals exactly 406 numbers perfectly divisible by 5. Stopping there would give us the wrong answer. Numbers like 25 or 125 contain bonus 5s that our initial sweep left behind. We add a second layer to our operation, dividing 2030 by 25 to extract 81 extra 5s. Pushing through the remaining powers, dividing by 125 catches 16 more. Dividing by 625 uncovers 3, totaling exactly 506 factors of 5. This method, known mathematically as Legendre's formula, systematically drains every single prime factor from the factorial, capturing them all perfectly without ever double counting a single digit. But remember, a trailing zero requires a partnership. We have our 506 5s, but we need to verify if we have enough 2s to pair up with them. We run the exact same layered sieve for the number 2. We divide 2030 by 2, then dividing by 4, dividing by 8, and by 16, working our way down through the powers of 2 up to 1024. The result is massive. We pull out 1015 from the first layer alone, accumulating a grand total of 2021 2s inside the sequence. Because every other number is even, the 2s vastly outnumber the 5s. The 5s are the scarce resource. They form a mathematical bottleneck. Since we only have 506 5s, we can only build 506 complete pairs. That means 2030 factorial ends in exactly 506 zeros. Now that we have a fully functioning algorithm, we can scale it up to an even more daunting target, 5,000 factorial. We can actually streamline our work here. Because of how numbers fall sequentially, factors of 2 will always outpace factors of 5. This mathematical breakdown shows exactly why. Approximating the sums using a geometric series shows the number of 2s grows roughly 4 times faster than 5s. Because 2s dominate by a 4-to-1 margin, checking the 5s is the only step that matters. So we run 5,000 through the 5 layers of our sieve. Dividing by the powers of 5 yields an immediate 1,000, then 200, 40, 8, and finally 1. Sum those layers together, and we know instantly that 5,000 factorial ends in exactly 1,249 zeros. Henri Poincaré described mathematics as the art of giving the same name to different things. We applied that here, treating a question about trailing zeros as a straightforward exercise in prime counting. By deconstructing a colossal factorial into prime components, we replace brute force calculation with a structured algorithm, making the end of an unwritable number entirely visible.